Happy Wednesday. Just two quick announcements here before I get started. Homework 9, your final homework assignment is now posted on Carmen. That's due on Monday. Sorry for the slightly later notice. I don't think it'll take you too long. It's not too involved. And then just a heads up that the final exam is coming up. It's pretty early in finals week. It's next Thursday already. So, and I think that's at 8 a.m. It'll be right in this room right here. And format will be similar to what you've seen before. You're allowed to bring a cheat sheet, all that good stuff. The coverage will be a lot of chapters here, 7, 8, 9, 12, and then 13.1 is officially on there. That's the very last part of this section of notes that we're working on right now. So I posted some other Chapter 13 notes that we might get started on today. We'll talk about on Friday if not. That stuff will not be on the final exam, but anything that's in the Chapter 12 notes that we're currently working through is fair game. And I will post some review exercises by the end of the week for sure, and we'll spend Monday doing some review of that stuff and looking ahead to the final exam. Any questions or comments about any of that stuff? We okay? Okay, well, yeah, we're going to pick up getting towards the end of the Chapter 12 notes here. Before we dive into some new material, I wanted to clarify something. I don't think I said this on Monday. So one of the sort of diagnostic tools we have here in simple linear regression is r squared, which you might see as lowercase r to the second power, capital R squared, or you might just see it written out r squared in the jump output. And we talked about where that came from. That involves the sum of squares that we have from the ANOVA table. And we talked about the interpretation of that. So that's the proportion of variation explained, proportion of variation in the response variable that's explained by the linear regression on the explanatory variable. But it's also, in this simple case here in Chapter 12, it is the square of the correlation coefficient. So that's kind of where the terminology comes from. Correlation, we use the lowercase r. R squared is the correlation squared. Simple as that. So if you know what r squared is, and you're asked to give the correlation, then you can take the square root of r squared. But remember, correlation can be positive or negative, so be a little careful about the sign there. Remember, the correlation talks about the strength of the linear relationship, so it can be if it's a positive relationship, the correlation will be positive. If it's a negative relationship, the correlation will be negative. So you can either look at the scatter plot and see which direction the trend is going, or you can look at the sign of the slope. That'll tell you if the correlation is positive or negative as well. So I think that's they ask you for that on one of the homework problems, or I ask you for that on one of the homework problems, and that's how you can find the correlation from the jump output. Any questions? Is that okay? So we'll look at an example when we'll actually do this here in a little bit. Okay, so here we want to quick finish up section 12.3, finishing up our discussion here on inference about our slope parameter, or the parameters in this model. So the last thing we did on Monday was we talked about doing a test or a confidence interval for beta 1. We often looked at whether beta 1 was either equal to 0 or not equal to 0. There's one other sort of test that we can do for the significance of a linear relationship here in regression, and that involves these two hypotheses here. So the first one is that the expected value of our y values is simply a constant, so it's just beta 0, or the alternative says that the expected value of our y random variable is this linear regression model that we've been looking at here. So it's beta 0 plus beta 1 x. And if you think about what these hypotheses are saying for this simple linear regression model, doing this hypothesis test is exactly the same as doing the hypothesis test we talked about on Monday, where you're setting beta 1 equal to 0 or not equal to 0. Certainly, if beta 1 equals to 0, then you can see how that simplifies to the null hypothesis here. If it's not 0, then we have the alternative there. So you might be wondering, if it's the equivalent to doing the other test, then why are we talking about a new one? Well, in the more general case, this is a framework we want to. So when we get into the chapter 13.4 notes, this will give a different result. For now, it is the same. But anyway, we can test these hypotheses using something called an F-test. So if we want to test these hypotheses, our test statistic is going to be, we'll call it the letter F, and it's going to be the ratio of mean squared for regression over the mean squared for error. And again, in the simple linear regression, the mean squared regression, the MSR is just the SSR. There's only 1 degree of freedom, so you're same. So there's that slight simplification there. And then this test statistic, lowercase f, follows an F distribution, which I don't think is anything we've actually talked about in here, but it's similar to a gamma. It's kind of it looks like a chi-square distribution, and doesn't really matter what the form of that distribution is. We'll use technology to help us find out what the p-value is. But anyway, whatever our test statistic is, our p-value will be the probability that an F random variable is larger than our test statistic. So we're kind of looking at, again, extreme values of our test statistic, same formulation. And then a fact here, again, for simple linear regression is that this F statistic, remember our T statistic was beta 1 hat minus 0 over the standard error of beta 1 hat. Well, F is actually T squared. So again, that's why these tests are equivalent in this simple case. These tests will tell you the same thing, and your test statistic are related to each other in that way. So again, the T ratio, this comes from testing the null hypothesis that beta 1 equals 0. So that's why we subtract off 0 there in the test statistic. Okay, so again, just trust me that when we get to a sort of more advanced case of this regression stuff, this will give us something different and will be something that's meaningful to talk about. But here in this simple case, it will tell you the same result as if you did the test we talked about on Monday. You guys who have taken your stats classes before, have you talked about the F distribution? Is this anything you've heard of before? Yeah? Okay. It's kind of another very, very common test here. It's often used in a regression setting. Okay. So let's go back to let's just finish up this example one more time. Let's go back to our example here where we're looking at the relationship between the efficiency ratio and the temperature. If we do the null hypothesis that the expected value of the efficiency ratio, that's what we're talking about. Yeah, expected value of the efficiency ratio is equal to just a constant, or it's equal to some linear function of temperature. That's kind of what we're looking at here. If you flip back to the jump output, so if you go back to the previous page of your notes, the F statistic from jump is 18.1019. So that's 1019. So that's from the ANOVA table, the analysis of variance section there, right in the middle. It lists this. It's the same table that lists the sum of squares, and then over on the far right side, it lists the F ratio. That is your F statistic here for this test. Okay, and it also gives also from jump we get the p-value. Also from jump here is something very small, so 0.0003. Which might sound familiar from the last time we did this test, the test for beta 1. Gives you the same p-value. Okay, so again, my p-value is really small. What is that? What's that? What decision am I going to make regarding my hypotheses? Everybody said we're going to reject, yes. So because the p-value is is so small, we will reject the null hypothesis. Okay, so the interpretation is going to be kind of the same as the other test as well. So what we said here is that I've rejected this notion that my expected value of y is constant as a function of temperature, and instead I'm saying that it's this linear function there. So what I've found is that there's significant relationship evidence that there is a significant linear relationship between these two variables, which is what the alternative hypothesis says. So so that is there is sufficient evidence to conclude that there is a significant linear relationship between temperature and the efficiency ratio. So again, rejecting the null hypothesis here in this case means that we have sufficient evidence to conclude that there is a significant linear relationship between these two variables, between temperature and the efficiency ratio. Okay, so if you're asked to say, is there a significant you're asked, is there a significant linear relationship, you have two options here. You can either do this test, or you can do the t-test for whether or not beta 1 is equal to 0. So you can either, first is a t-test of beta 1 being equal to 0, or you can do the f-test, which says that the expected value of the y is just equal to beta 0. So again, the interpretation will give you the same answer. You just need to use one of those tests. Both of those will allow us to say that there's a significant linear relationship. Yeah, Jamie.
How exactly did we use the F statistic in this?
How did we use the F statistic?
Was there a table we went to go look at to get this p-value other than jump output?
So you could, if you look in the back of your textbook, there is an F distribution table. So the F distribution, it depends on, the T distribution depends on the degrees of freedom. The F distribution depends on actually two different degrees of freedom. So so that the F ratio you see is the mean square and for regression over the mean squared for error. Both of those have a corresponding degrees of freedom. So you need to figure out what two of the degrees of freedom are, and then find the right spot in the table, and it's a giant mess. The table kind of becomes really cumbersome in that case. But yeah, if you want to check that out to kind of convince yourself that that's what's going on. So this depends on 2 degrees of freedom, and yeah, it's just very messy to actually use the table to find that. But that table is in the back of your book as well if you want to check that out.
P-value should be the same.
Exactly, yeah, yep. Again, like when you're finding p-values for the t distribution, the degrees of freedom you want isn't always exactly there. So there's again some estimating going on, some approximating. What I just said and what JMP will give you is the exact p-value. So that's again another reason, I guess, to use the technology output. Yeah. So p-values are found in different ways depending on the distribution of your test statistic, but it always means the same thing. So I think once you kind of get a good understanding of that, when you encounter p-values later, you should have a good understanding what that means. Good question. Any other question you guys can think of or comments? No? Okay. Let's forge ahead then. Section 12.4, I neglected to take it out of your notes. I think we're actually going to skip over this one. We can also, so far now in regression we've done inference on our model parameters, and we've done sort of like an overall model test with our f-test here. You can also do inference for estimated y values. So again, we know what our estimated linear regression equation is. It's y hat equals beta 0 hat plus beta 1 hat times whatever x value you're looking at. So I think as we've sort of done already, you can use that to get an estimate or a prediction of what the y variable would be based on a particular x value. I think that's pretty straightforward. But you can also then create a confidence interval for that estimate or that prediction. The formulas are such that you never really do them by hand anyway, and so I'm gonna skip over that section. You can look in your notes if you want to read a little bit more about that. But again, if I ask you to estimate or predict whatever y is for a particular x, call it an x star. Again, you just plug that x value into your estimated regression equation. That gives you your point estimate. Then what I'm going to skip in the notes is how you would calculate confidence intervals for that. I'll let you guys take a look at that if you're interested. Okay, so jumping ahead to section 13.1, I think this is the almost the last page of our notes here. You might be, I'm sure you're all very concerned about what we've been doing so far here, because previously we had lots of conditions to check, right? In chapters 7, 8, 9, we always were checking conditions, and we haven't really checked any conditions here. So don't worry, we're coming back to it now. This is kind of sort of in this setting, it's more of an assessment for the model that we put together here. So in previous chapters, we checked conditions prior to doing our inference, or prior to doing a confidence interval or a test. We checked our conditions. Here in regression, we will more do our checks or our assessment after we've fit the model to kind of then know if it's okay to use the results that we've gotten. Okay. And the reason for that is that looking at the original scatter plot is sometimes kind of hard to tell if your model assumptions are going to be appropriate. So you more need results from the model rather than the raw data itself. So it's getting into this idea of assessing our model, or kind of saying if it's an adequate model. Okay, so the main assumptions that we make in this model in this chapter are, again, this first one, that the relationship between x and y is linear. So that's our first assumption. And the second one is that the error term that we have floating around there follow a normal distribution. So here's number 2. The errors have a normal distribution. So those are kind of the two main things that we need to check. Again, the point is that x and y could be related, but not in a linear way. So that's just something we need to make sure that a linear relationship is in fact appropriate here. And then we also want to make sure that this assumption of normal error terms is good as well. And so we'll assess the accuracy or the adequacy of our model using the residuals, which I think we've talked about before, but we'll call them. We'll use a lowercase e to represent that. And again, remember, that's just the observed value minus the expected value or estimated value. So our residuals are just your observed minus your expected, and that's what we will use to check these assumptions. Okay, so there's three sort of main plots that we'll use to assess the validity or the usefulness of our model here. First, we'll look at our residual plots. So we'll put the residuals on the y-axis, and then we'll plot those against either the predictor variables x or maybe the fitted values y hat. We can also make a plot of our predicted values versus the observed values to kind of see what that tells us. And then finally, we will use something called a normal probability plot of the standardized residuals. So again, these first two will tell us or allow us to answer the question, is a linear relationship appropriate? And this last one will help us check the normal error terms. That will allow us to say whether that's an okay assumption or not. Okay, and I think I mentioned to you a normal probability plot before. I don't think we've actually talked about it, so I'll show you some examples here and kind of what we'll be looking for there. Okay, so then just in general, what we're able to say based on these plots is the number of these things. So either the relationship is not really linear, maybe there's some other relationship that would be more appropriate. We can say things about, so maybe the error term does not have a normal distribution. I guess implicitly we've also assumed that the errors have zero mean and constant variance. We can look at that. We can also use these to help pick out outlying values, see if there's any outliers floating around in our data set. Okay. So let's look at some examples of what your book says are good diagnostic plots. So again, here at the top, this first one, where we just have listed the scatter plot with the fitted regression line. And this is the residuals on the y-axis versus the predicted values. Okay? And what we're looking for in this residual plot is sort of no pattern. So in this residual plot, we want to see so again, if there's sort of just random scatter in the residual plot, that tells us that a linear relationship is an okay assumption. So no pattern tells us that, sorry, running out of space here, that a linear this linear relationship is in fact appropriate. And I think all of you would have said that from just looking at the scatter plot too, that that's a very strong linear relationship between those two variables. But again, the residual plot sort of makes it easier to see that trend if it happens to not be the case. Okay, so when we're looking at a residual plot, we want to sort of see nothing, and that will tell us that the linear relationship is appropriate. Again, that the top left plot there is your predicted values versus your observed values. Again, you would want to see a nice linear relationship there. So again, we want you would hope that your predicted values are going to be close to what your observed values are, right? And actually, the top right there is just another residual plot. It's the standardized residuals against the explanatory variable instead of the predictor variable. So that'll tell you the same thing. So we want to see no pattern here. And then finally, at the bottom there, we have a normal probability plot. And so again, what this plots is it plots the standardized residuals against sort of their standard scores to kind of see if we have that nice the nice linear relationship that we want to see there. So in the normal probability plots, again, we want to see a linear relationship. And again, it's not going to fall exactly on a line, but because this is kind of in a very sort of tightly clustered area there along that line, this means that the assumption of a normal distribution for our error terms is an okay assumption. Okay, so this will tell us that it's that assumption that we made about our errors having a normal distribution, which is sort of the foundation for everything in this model, that's an okay assumption. So we're looking for a sort of straight line relationship in the normal probability plot there. Okay, well, let's also look at some bad residual plots. So let's see, what do we have here? I think these are all residual plots. The residuals against the explanatory variable, and I guess except for that lower right one. So if you see something like this in the upper left here, this tells you that you have maybe a nonlinear because there is sort of that curved pattern going on in your residual plots. So because it's kind of in this parabolic shape there, that means that your relationship is not really linear. If you see a residual plot that looks like this, where it sort of increases as your x variable increases, this tells you that you have a non-constant variance. So we assume the residual terms are IID normal with mean 0 and variance sigma squared. So we're assuming that they all have the same variance, and if your residual plot looks like that, then that means that they don't all have the same variance, that variance is different, and that's sort of a bad assumption there. So that's a violation of your assumptions. And also this lower left one now, when we have this point floating around, this is an outlier which could have bad implications for your regression model. So this could be So again, looking at the residual plot, you can maybe see that is an outlier, and that you should maybe go back and look at that. Maybe the data was entered wrong. Maybe that data point shouldn't have been in your data set, or maybe that outlier is meaningful, and you might want to say something about it. But anyway, these are sort of three things that you would hope not to see in your residual plots. Sort of a non-random scatter. We have a non-linear relationship, or if the variance is not constant. And then also looking for outlying values. And I think this lower right plot is just showing you the effect of an outlying value. So when you include the outlying value, this is your linear regression line with the outlier. And if you don't include it, then this is without. And that shows you that relationship is very different if you include the outlier versus if you do not include the outlier. So outliers can be a big problem. Okay. Any questions or comments you guys can think of? Okay. Well, let's wrap up our example by making sure that what we've looked at is okay so far. So we can get these things out of jump. Here we have our actual our actual y values against the predicted values. And then also there's our residual plot versus our predicted values. And we can also look at a normal probability plot. So it's a little bit harder to get this out of JUMP, but you can still do that. So again, maybe kind of hard to see, but the normal probability plot here. Again, it gives you that straight line where you want to see your residuals kind of clustered around that line to let you know if the normal assumption is okay. So again, let's start here. Let's start with our actual observed y values against the predicted y values. Again, what do I hope to see in that first plot on the left here? So regardless of what I do see, what am I hoping to see in the actual versus predicted? Yeah, I want to see a linear relationship, and specifically one that sort of follows that 45-degree diagonal there. So what do you think? Yeah, not very good, right? This is a little concerning. This doesn't look very good. So it maybe calls into question the linear relationship between these two variables. So that's maybe a red flag, cause for concern there. How about the residual plot over here? So if we look at over here on the right, again, what am I hoping to see with my plotting my residuals versus my predicted values?
No pattern.
Yeah, I'm hoping to see no pattern. So what do you guys think? Do you see a pattern there?
Spreads out to the right.
Yeah, right. I mean, it's a little hard to say, but it might kind of have this that kind of shape going on there. I don't know. It's. I would say again, we don't want to overinterpret these things. So I would probably find that a little bit concerning, but not too bad. But you're right. It does show us a non-constant variance. So this shows. So maybe that's something we need to revisit here in our model here. And finally, how about the normal probability plot? What am I hoping to see in here? Yeah, right. I hope to see all my residuals sort of falling more or less around that diagonal line. And what do you think? Yeah, that's actually pretty good. Again, there's also JUMP also provides you a histogram of the residuals. So you can imagine that flipped on its side, and does that look like a normal distribution? Well, there's maybe some holes in there, but this actually looks pretty good. I would say this is a good. So maybe in fact the normal assumption is an okay one. Okay, so if we were actually trying to use this model for something, we might want to go back and kind of address some of these assumptions. There are ways of dealing with, if you have a problem like this, there are ways of addressing those. We'll get to that a little bit in the next section of notes. Any questions or comments about residual or diagnostic plots here? Okay, so if I ask you to assess the model based on the plots, this is exactly the kind of thing you're going to do. So, were my modeling assumptions appropriate? These are the ways that we can check those assumptions. Okay, I wanted to take. Okay, before we move on to the next chapter, I wanted to do an additional example. Again, this was another extra credit submission that I thought was interesting. In summary, before we get to that, this is what I just said. So in addition to all the inference that we might do, so confidence intervals, hypothesis tests, all that stuff, again, we want to make sure that our model is appropriate. And we can do that by a few things, looking at R squared, making sure R squared is big enough or not small. Hopefully it's closer to 1. Again, then looking at our residual plots and then looking at our normal probability plots. So these are the kind of things you want to say if I ask you to assess the model. Okay, so another example here, one of you guys submitted data from the Cleveland Cavaliers. Do you have any other Cleveland fans in here? I'm a Cleveland. Yeah, here we go, Devin. Represent. So again, we all know that trend in sports here is doing analytics, right? So this is a way that we can maybe do some analytics for the Cleveland Cavs. So the organization wants to improve their team performance. They need to improve, right? And they've asked us to kind of identify important skill sets from players on their team that have led to success in the past. So the data that we have, I think whoever submitted this got this from ESPN or something like that. We have data on a bunch of years from the Cavs from 1980 to 2010 on a whole bunch of variables. But what we'll consider here is 2 particular ones. We're going to try to predict how many wins the team had based on one of 2 explanatory variables. So we'll do 2 separate models and kind of compare those. So we're going to look at 3-point shooting for the team and also the number of turnovers they had. And in a few slides, I'll show you some jump output that we can look at the usefulness of these things. Okay, so before we do that, I wanted to put up here some scatter plots here. So on the left side here, I have wins against the 3-point percentage. This is all the observations that I have. Then I also have the wins versus the turnovers that the team had over the course of the season. So my question for you is a linear model for both of these cases? Is a linear model appropriate? So let's start with 3-point percentage. What's the relationship between 3-point percentage and wins there? So when you look at a scatter plot, you want to talk about the strength, direction, form. Is it linear or nonlinear? And then are there any outliers? So what would you say about the one on the left here?
Moderate strength.
Say it again.
Moderate strength.
Yeah. Okay. It's a moderate strength. I would agree with that. It's not very tightly clustered around that line. But what direction is that relationship? Positive. Yep. Larger 3-point percentage corresponds to more wins. Is a linear relationship appropriate?
Probably not. Looks a little bit more clustered towards the top.
Yeah, again, maybe not. We maybe have some more points up here. So maybe not exactly. But again, I would say we don't want to overinterpret these things. So I would say that's actually a pretty good linear relationship there. Aside from maybe some values that, like if you cover up a few values, maybe it looks more linear. So I would say that's pretty good. So this is looking moderate. It's positive. And I would say this is a linear relationship. Do you notice any outlying values in there? Any data points you should be concerned about? This one over here? Yeah, that's maybe a little concerning. Again, I would say there's nothing too crazy going on there. Again, the point is kind of out there, but it's also sort of in the trend of the data, right? So it's kind of out there by itself, but it's not sort of bucking the trend in some ways. So I would say that there's no outliers in here to be concerned with. All right, real quick, let's look at the other one. So if I look at the wins versus the turnovers, again, what can you say about that? Strength, direction, form.
Looks like the outliers influencing it a lot.
Yeah, so this point over here might be concerning, right? So if you ignore that point, well, it's definitely negative, right? That relationship is going downward. And again, linear, I would say, is not a terrible assumption, but we definitely have an outlier floating around in here. So this is, again, maybe sort of a moderate strength, negative relationship. And I think linear is okay. But we have an outlier. And that outlier is definitely influencing. It's kind of pulling that regression line. You could, if that point wasn't there, the line might be something more like that. So that's maybe a point to look at and take out.
Would you just throw that out if you were really wanting to analyze this for useful purposes? Just take that one data point out.
Yeah.
Jump, disregard.
So that's what I did. But in general, yeah, when you have an outlier, it is very important to go look at this. So kind of see if there's a reason that point is somehow different. So if there's a reason you can find that explains why that point is different, like well, that point is from 1998-1999 season. Again, I don't know enough about the season to know if there was something different that was going on there.
That was like a shortened season.
Was that a shortened season? Okay, well then that would be why. And I think we're looking at a total turnovers here, so that would be. So there we go. So there's why I removed that point. But the point is, if you see an outlier, you should go back to your data and look at what's going on with that point. So if there's some reason you can find that cause you to throw that out, then you should absolutely throw it out. On the other hand, that point may have there may be a reason that was low. Maybe there's something that was going on there that is important to look at in this model. So if you have an outlier, take a look at it and see if that has any information for you. So does a linear regression model appear to be appropriate? I would say yes. Okay, so here I've now taken out that outlying value and I ran the regression models in JUMP. And so here's some output. So I'm telling you the linear fit of each of those models, and then I also have the R-squared values. So now might be a good time to double check that we can calculate the correlation from this output right here. So let's say what the correlation is here. So the correlation R is again the square root plus or minus the square root of R squared, right? So this is the square root of R squared, so 0.4026. And will that be positive or negative correlation? Positive. Why positive? The relationship is positive, right? Exactly. So this is I think this is 0.6153. Similarly, over here, the correlation is again the square root of R squared. It's the square root of 0.317571. But now the correlation will be positive or negative? Negative, right. So this is negative 0.5635. Okay, so if you wanted to predict the number of wins that the Cavs were going to have based on one of these two things, which one would you prefer? 3-point shooting, and why do you say that? Yeah. So stronger relationship, R squared, you're explaining a higher proportion of the variation in your wins by the 3-point percentage shooting, and also the correlation is higher. So if I was going to pick one, I would go with this one, since correlation is higher and the R squared is also larger. Okay, so let's pick that one and go forward here. Oh, I also wanted to show you these residual plots. So again, at the top I've given you the residual plots for the residuals versus the predicted, and same on the other side there. And then I've given you the normal probability plots. Do you see anything concerning going on here? Normal probability plots look good for both of them, right? Residual plots, they're maybe a little weird. again, you have maybe that point is causing that to look a little bit strange, but I would say these residual plots are fine. So again, looking at the previous slide, if the correlations were as they were, but one of these plots looked really terrible, for example, then that would maybe help you choose which model to use as well. Again, I think we can stick with these plots don't look concerning. I think we can stick with the 3-point percentage shooting here. Okay, so ignoring that one season as an outlier, we'll go with the 3-point percentage model here. So on your homework, I ask you to fill in the regression table, fill in the ANOVA table, the analysis of variance table. And so I think I've given you results that look sort of like this. So we need to fill in we need to fill in 5 things here. And how can I go about doing that? So how can I find what the error sum of squares is there based on just this information? Yeah, right. So remember, the error sum of squares is equal to the total sum of squares minus the regression sum of squares. So here that's 5019.37 minus 2021.1842. So that should be 2998.18 or thereabouts. Okay, and then what about my degrees of freedom? If I have, how many degrees of freedom does my model have? Anybody remember that? Degrees of freedom for the regression sum of squares? 28. So 28 is the answer for one of those blanks. Yeah, the model only has 1 degree of freedom, and the error then has 28. So again, your degrees of freedom should add up as to your sum of squares. So the total line there should be the sum of the first 2 lines there. And so again, using just this information, how many observations do I have? What is my total degrees of freedom with respect to my sample size? Yeah, so this is this here is n minus 1. Your error sum of squares is n minus 2. So therefore you have 30 observations. So just to check that, remember where those numbers are coming from. Okay, so then what goes in the mean square column? What number goes there? What 2 numbers go there? I guess we have 2 numbers to fill in. So the mean square for regression. Yeah, so the mean square for regression equals the sum of squares for regression divided by its degrees of freedom. So that's the same. And similarly, what's my mean square for error? Well, again, it's my error sum of squares divided by its degrees of freedom. So divided by 28. So that will be 107.08. Okay, and then my F ratio. What's the F statistic? Yeah, right. So this is mean square for regression over the mean squared for error, and that test statistic then is 18.876. And then the p-value there is provided as well. Yeah, Kevin.
When is the model of degrees of freedom not 1?
When is the model degrees of freedom not 1? When you're not doing simple linear regression. So again, the next section notes that we'll get to has you might have more than 1 degree of freedom for your model there. You can sort of think about that as how many predictor variables do you have? So here we have 1 predictor variable, so there's 1 degree of freedom. Yep. Okay. So is there a is there a significant linear relationship between 3-point percentage and wins? What do you guys think? Looking at the analysis of variance table there that we just filled in, as well as the parameter estimates. And there's two possible answers, two possible ways to answer this question. Who can tell me one of those ways? So what's the first way that I can say if there's a significant linear relationship between these two variables? T-test, absolutely, yeah. So the first way would be test the hypotheses, beta 1 equals 0, that beta 1 is not equal to 0. Your test statistic here is 4.34 with p-value of 0.0002. Therefore, you would reject the null hypothesis, say that that slope parameter is not equal to 0, and that there is a linear relationship. So, so you would reject, again, which said that there is some linear relationship, again, between 3-point percentage and wins. Okay, so that's one way. What's the other here equivalent way of testing that? Is there a significant linear relationship? F-test, exactly right. So I want to test that the expected value of my wins is equal to just a constant versus it's equal to this linear relationship. Again, your test statistic is up here. It's 18.89, and your p-value again is same thing. So you'll make the same conclusion. You'll reject the null hypothesis and say that there is a significant linear relationship. And again, F statistic is the square of the T statistic. So T is 4.34. Square that, you should get 18.89. Okay, so we sort of move past a lot of the steps that we were doing earlier with actually calculating the test statistic and finding standard error and everything like that, and we can just use the output to, again, identify the hypothesis test that we want to do, write out your hypotheses still and all that stuff, but then use the output to tell you what your test statistic and p-value are, and then you still need to make an interpretation there. Okay, one more thing here. Just to kind of wrap this up, so suppose the Cavs are shooting 35% 3-point percentage. How many wins would I expect them to have for a season in which they shoot 35% from the 3-point line? Well, my prediction again is just going to be is y hat. It's going to be beta 0 hat plus beta 1 hat times 35% or 0.35. And just to remember, where can I find beta 0 hat and beta 1 hat? Yeah, parameter estimate. So this is just negative 15.5 plus 161.57 times 0.35. So if they shot that, we would expect them to have about 41 wins on that season. So that's kind of a very quick rundown of what you might do with a regression model. Again, is there a linear relationship, and then use it to make predictions. So yes, I'm out of time. Thank you guys for being here, and we'll see you on Friday.